And of course, as usual, we are grateful to the La Pietra families for funding and financing this activity. And unfortunately, they had previous engagements and they could not join us. I'm really happy that we have such a big audience because we were fighting yesterday the elements and today St. Valentine. So it's almost an uphill battle, but fortunately I'm glad to see that many people are joining us for this lecture. And it's a real pleasure and an honor to have Professor Dame Jocelyn Bell Burnell, who is an excellent astrophysicist and cosmologist. She's made fundamental discoveries, but is also someone who is extremely engaged in equality, in diversity, in promoting science for women, etc., etc. And she's going to tell you a story that most of you probably know, but she will give you some additional details that I'm sure you're going to be very happy to listen to. So please, Jocelyn, thank you. Thanks.
So, as I say, this is a story, late 1960s, back in Europe in the British Isles. I've done an undergraduate degree in physics, so whether I can get this audio file to work, of course, is another question. So supposing you take a whole lot of satellite TV dishes, a couple of thousand would be good, join them up together, low-loss cable, plug them into an excellent radio receiver, point at a carefully chosen piece, this guy you might hear. Okay. What you might hear is a pulsar, which would sound something like brrrr, or bop, 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 or or even whee, depending on the period of the pulsar signal, which in turn determines the frequency. It's a more or less single note. Of course, that's all with hindsight. At the time, it was a lot less clear what we were doing. So this is a story about radio astronomy, astronomy using radio wavelengths. Electromagnetic spectrum shows all the possible wavelengths. This is the bit our eyes see. We're clearly rather deprived when it comes to the spectrum. We only see this tiny bit. If you come to the left of the visible, out the red end, you come to infrared, then millimeter waves, and then radio. We now do astronomy right across this spectrum. Some of it you have to get up in space to do, but we do now do astronomy right across that spectrum. And indeed, just recently, there's a whole new spectrum opening up called gravitational radiation. So it's an exciting time. But I'm going to be talking mainly about radio astronomy, which is at this end. And radio wavelengths are a lot longer than optical wavelengths, so the kit is much, much bigger than an optical astronomer would use. And you've maybe seen pictures of some very big radio telescopes. So I think this is Greenbank, if I remember rightly. This is Jodrell Bank, University of Manchester in England. This is the Bonn radio telescope. And this is the Cambridge radio telescope that I built. And it's clearly of different design. It's because it works at a longer radio wavelength, and it doesn't need a solid surface reflector behind the antenna, whereas each of these will work at shorter radio wavelengths than I was using. So it's a story, and I'll try not to take too long over it, but I do tend to hang it on a bit. I started life in the north of Ireland. That's the bit where the Protestants and the Catholics fight each other, and which has been without a government for the last 2 or 3 years until just a couple of weeks ago. Charming part of the country. I had some of my education in York in the north of England. I did my bachelor's degree in Glasgow in Scotland. I've been in the north of the country, the heathen part of the country. And then very much to my surprise, I find myself in Cambridge to do a PhD. And I've got an accent, and I come from the wrong part of the country, and I've got the wrong background, and I'm clearly heathen and ill-educated. And it was quite daunting. There would be young men full of confidence, striding along the streets, talking in very loud voices about what Pliny said or something like that. And here's me from the north of the country, not even quite sure I know what Pliny said. And I've done a physics degree, quite a good one, but I think they've made a mistake recruiting me. Don't think I'm bright enough for this place. They're probably going to throw me out. They'll discover they've made a mistake. So what am I going to do about it? I decided, yep, they probably will throw me out. They have made a mistake recruiting me. I'm not bright enough. But until they throw me out, I will work my very hardest so that when they throw me out, I won't have a guilty conscience. I'll know I just wasn't bright enough for this place. And if any of the students here find themselves somewhere where they're overawed, that's quite a good strategy. Do your best until they throw you out. And actually, they probably won't throw you out. Whoops. So, having done a bachelor's degree in Glasgow, which was quite tough, in the sense that I was the only female in the class, 59 men and me. And it was the tradition in Glasgow that whenever a woman entered the lecture theatre, all the guys would whistle and stamp and catcall. And we had wooden lecture theatres, so they could make quite a noise. It was fine in the junior years. There were several women doing the same subjects. We gathered as a group outside the lecture hall, entered as a group. But for my final 2 years, I'm the only female in this class. And so I have to face that horrendous taunting on my own. I did learn to control my blushing, because if you blushed, they only made more noise. They were winning. So that was quite an achievement. I could enter stony face, pretend I hadn't heard anything and take a seat. All our lecturers were male. We did actually have one woman. She survived one lecture and quit. I think if that happened in a university today, the university authorities might say something, do something, but back then they didn't. Anyway, I guess I've become quite tough surviving that lot, getting a reasonable degree and getting a place in Cambridge to do this PhD in radio astronomy, which I'd wanted to do since I was about 16. And because I've worked one summer at Jodrell Bank, I'm given first choice of project, and I opt for a project to find more quasars, quasi-stellar radio sources. They were very new back then, very few were known, and what we did know was they were very strong radio sources, and they were very, very distant. So they're very strong radio sources in spite of being very, very distant. And they looked quite compact. Optical astronomers thought they were looking at stars until they managed to get an estimate of the distance and realized that was no ordinary star. So there's probably about 20 quasars known when I start. And by the time I finished, I've got the number up to 200, so that was fairly satisfactory. But I spent the first 2 years helping build this radio telescope. And because of its long wavelength, it's not obviously a radio telescope. The slanting bars carry a reflector, so it's looking primarily up in this direction. This is to the south, and it's looking where the sun is typically at midday in the south. It's that angle above the ground. There's a whole lot of copper, as you can see by this wonderful oxidized stuff, rows and rows of antennae, feeder wire, more feeder wire, ultimately into cables, ultimately back to receivers and recorders and so on. Almost 200 kilometers of wire and cable in that thing. And I spent the first 2 of my 3 years helping build this thing. And for the final year, I was left on my own to operate it. 2,000 odd antennae, an area of 57 tennis courts. At that time, the University of Cambridge had one computer. It was made with vacuum tubes, not transistors, and it occupied a whole room, and it had less memory than your laptop, and that was for the whole university. It was fairly experimental. It worked mostly, but yeah, it worked more or less. But I didn't have time on it. My supervisor didn't have time on it. Our data came out on paper chart, long, long rolls of paper chart, red ink paper charts. And you can see here in the image, I'm busy analysing some of this paper chart. I had over 5 kilometres of paper chart by the end of my survey. And remember, I know they're going to throw me out, and I'm working very, very hard so that when they throw me out, I won't feel guilty. And I'm checking every flippin' millimetre of those kilometres of paper. And I quickly get to recognise the quasars. That's what I'm meant to be working on. In fact, I found something like 200 more quasars. Got the number up from about 20 to just over 200, so quite satisfactory from that point of view. And there's quite a lot of radio interference because it's a great big radio telescope. It's very sensitive. Cars were badly suppressed. They gave out radio waves. Taxi radios, pirate radio stations, all sorts of things gave interference. Now, you very quickly, when you've got that quantity of data, get to know what's normal and what's abnormal. And in amongst the quasars and in amongst the inevitable radio interference, there was occasionally some signal that I couldn't make sense of. So here's a bit of radio interference, and here's, I think, the first instance of that funny signal. And they look different. I'm going to unpack why they look different, because I wish somebody had taught me this when I was an undergraduate. Here, the spikes go up and down. Here, the spikes go mainly upwards. Here you can see chart between the spikes. At least here at the left-hand edge, the spikes are so close you can't see chart between them. We're commenting on the amplitudes present and the frequencies present. That is Fourier analysis. You've just done Fourier analysis in your head by looking at those recordings. Interference, inevitable. We've got this enormous radio telescope, and even without things like pirate radio stations and badly suppressed taxi radios and things like that, there's inevitably bits of radio interference. So I was quite happy with that. I wasn't at all sure what that was. But your brain stores an amazing amount of information. And even though by now I have several miles, literally, of this paper chart, the brain says, you've seen something like this somewhere before, haven't you? You didn't flag it up, but you saw it. And so your first stab is to say, wonder if it came from the same bit of sky, and get out the chart recordings that cover that bit of sky from previous observations. Yeah, it was there. I sort of registered, but I didn't log it. Not there that time, not there that time. Might have been there that time, don't think I noticed that. Not there, not there. And here's this one. But when it's there, it's coming in at the same right ascension, which is like longitude on the sky, and it's coming in on the same declination strip, which is like latitude on the sky. When it's there, it's coming from the same bit of sky. So at this point, you have to involve your thesis advisor. Tony, what do you think this is? Huh, how the heck can I tell what it is, you stupid woman? It's all jammed into about 1/4 of an inch. We need an enlargement, obviously. Well, one quite neat thing about chart recorder technology is enlargements are easy. You run the paper faster under the pen, and it all gets spread out. Except you can't leave the chart recorder running at that speed forever, or it gets through a whole roll of paper in about 20 minutes. And guess who has to live at the observatory putting a fresh roll of paper in every 20 minutes? Not such a good idea. Next best idea, grad student goes out to the observatory about this time, switches the recording to a higher speed, switches it off about there, and then gets on with the rest of their work. And I did that for probably about 10 days and made high-speed recordings of receiver noise. The thing, whatever it was, had gone away. And of course, that's the grad student's fault. If you're thinking of being a grad student, fine, go for it, but you will get the blame for quite a few things that aren't really your fault, because your thesis advisor has to vent their fury somewhere, somehow. So, I persist, keep going out, trying to get this high-speed recording, and ultimately, I get one. Along the bottom are 1 second time pips. Along the middle, or upper part, is the enlarged version of the kind of thing you were seeing on the previous chart. The name was added later. That's my thesis advisor's handwriting. And you can see that there are regularly spaced pulses, a gap, quite a few regularly spaced, maybe several gaps, and then maybe a few more. And from the 1 second time pips, you can see the period is about 1/3 of a second, 1 1/3 seconds. That's a bit surprising. So I take it to my thesis advisor, who says, expect you've connected the thing up wrongly. Comes out to the observatory next day at the appropriate time, watches while I set up for this special observation, agrees that I have wired it up correctly. And fortunately for me, it comes in with this kind of bip, 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 bip signal again. And what's more, it's bip, bip, bipping as the same rate as it was the first day, about 1 1/3 seconds. So what's this? It's unique. Doesn't sound like interference. Are we picking up signals from some of the other equipment on site? Have some other scientists in Cambridge got a program going that gives regular pulses? Well, actually, it would have to be other astronomers, wouldn't it? Because this is keeping constant right ascension, constant position amongst the stars. So all other astronomers in Cambridge deny having had any program going for the last few months that could possibly cause radio interference. But it is keeping to this 23-hour, 56-minute day. So it's not Joe Doak driving home from work in a badly suppressed car. He's getting off work 4 minutes earlier a day. This has been going on for about a month, and his employer hasn't commented. Doesn't sound like it's that kind of interference. Anyway, Jocelyn, keep observing it. So I keep observing it. And we, somewhat in confidence, because I think Tony still thinks he's got a daft grad student who's doing something stupid, so we don't shout about it. But we gradually start talking to other radio astronomers about what this might be, you know. Who could have had a program going? Well, there's the optical astronomers. They're always a crazy lot. I wonder if they've had any program going, but no, of course we haven't. Always deny causing interference, incidentally, and then go check quietly. But so Jocelyn, keep observing. Yes, okay. And keeps pulsing at the same old rate. And it's not making sense. I pick up the first pulsations sort of September time. And because of all these extra observations, the routine data analysis is falling very, very far behind. And one day, just before Christmas, I'm busy catching up with some of the routine chart analysis. Oh, yeah. Oh, it's not it. It's a different one. A total. Oh, I wonder if I've seen that before anywhere. Get out the chart recordings that cover this part of the sky, lay them out on the floor. Grad students were in a big attic and we had a corridor about this length between all our desks. So it was great for laying out these charts. So get out the charts for this second candidate. Ah, this might be another one. It's not there as often, but it's on that one. No, no. Might be there. No, there. Didn't notice that one. No, no, no. Might be there. And here's this one. And they're all at the same time, the same right ascension. And I'm on the same declination strip. Aha. That bit of sky will be seen by the telescope at about 11:30 tonight. I was reckoning to work late tonight because I'm going on vacation tomorrow. I'm going on vacation with my boyfriend, to my parents, and with a ring in our luggage, because we're going to announce our engagement. And I kind of have to be there. But, okay, this thing's going to transit about 2 o'clock in the morning. I've got to be out at the observatory. I leave Tony a rather elliptical note, think I've got another one going out to the observatory at 2 a.m., blah, 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 blah. And I go out and in comes pulse, 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 pulse. Slightly different period, slightly different repetition rate, totally different bit of the sky, but sufficiently similar that I can say, yeah, it's another of whatever these are. I leave the recording on Tony's desk. He's agreed to keep the survey running while I'm away on vacation. And go off on vacation, we duly announce our engagement, and I come back sporting a ring. The daftest thing I ever did. Married women didn't work. Everybody knew that if married women worked, the household would fall to bits and the children would be delinquent and blah, 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 blah. So it's a signal that I'm giving up work, which my supervisor duly noted. It wasn't actually my intention to give up work, and I didn't, but that was the signal I realized afterwards I was sending. Anyway, Tony very kindly kept the survey running, piled the charts unanalyzed on my desk. We went to my parents, we announced our engagement, came back. And when I got back to the lab, Tony was in a meeting. I couldn't speak to him immediately, but there's a huge pile of charts on my desk because he's just dumped them there. And I sit down to do some more of this routine chart analysis. And I'm working through yet another strip, another declination strip. And, oh yeah, which one's that? It's not. It's not either. Wow. I'm pretty certain I know how that'll behave when I get a fast recording, but I'll need to get a fast recording. And perhaps I should just check back that I've been seeing it previously at this time. And I had. Okay, I will just finish this. There's about 2 meters left. Just finish this roll, and then we'll think what next. And I'm working on what? 1, 2, on the same piece of chart paper, same declination strip. Ye gods. At that point, Tony appears from his meeting, stands at the end of the desk. Look, Tony, look. Oh, Happy New Year, Tony. Thank you for keeping the survey running. Look. Huh. How many more have you missed? Go back through all your old records. There were literally several miles of paper chart by that stage. And I did go back through all those miles of paper chart, and I could see occurrences of these 4 things. The 4th one was particularly exciting because it had a much faster period than the others. The others were all about 1 1/3, 1 1/4 seconds. This was just 1/4 of a second, much faster. And whatever it was clearly going to drive the physics quite strongly. So we had 4. Jocelyn, keep the survey going. Keep your eyes open. There might be more. You never know. And if you've got time, check back through all your old records, because you never know how many more you've missed. So I had plenty of work to do. But we ended up with 4. And 3 of them were periods of about 1 point something seconds. The 4th one was a period of just 1/4 of a second. And Jocelyn, keep working on your thesis. You know, you need data finding these quasars. That's what your thesis is about. But meanwhile, we're also doing all these special recordings of these new objects. And come the time when we have to publish, we decide to publish the first one first, and 2, 3, and 4 will be in a second paper. And we duly write the paper and show it in confidence to a number of our colleagues. While we only had 1 of these, we were fairly cautious about talking about it. We never talked outside the radio astronomy group about it. It was top secret, but within the group, we could begin to ask colleagues, what do you think it could be that gives a regular signal with a period of about 1 second? And got various not terribly helpful suggestions. We ended up with 2 possible models. Let's see. Yes, okay. We did enlist the help of a colleague and his grad student who had another radio telescope, separate receiver, also working at the same frequency. And I remember that rather vividly. We were looking at the first candidate at this stage. And the grad student on the other project was called Robin. Paul Scott was his supervisor. And Robin's telescope also worked at 81.5 megahertz, but it was slightly differently orientated. So it would see the same bit of sky as my telescope, but about 20 minutes later. Robin and his thesis advisor, I and my thesis advisor were all out at the observatory for this particular observation. My telescope saw the thing, it was pulsing away nicely. And then Robin ran up his telescope and started looking. And nothing happened, which was horrible. And the 2 academics start walking down this long lab. Now, what could it be that shows in your telescope but not ours? Could it be da-da-da? And I'm tracking along behind, trying to keep up with this. Robin stays by his pen recorder. Could it be? No. And suddenly there's a shriek, here it is! And we all go rushing back. Robin had miscalculated by 15 minutes when his telescope would see the object. If he'd miscalculated by an hour and 15 minutes, we'd have all gone home, and the story would be different. But here's the signal coming in from a separate radio telescope with a separate receiver and a separate pen recorder. And it's showing exactly the same pulse period as I was getting. So it's not that Jocelyn has wired the telescope up wrong. Hooray. Still a number of questions to answer, but at least that's one that's very nicely nailed. One of the postdocs was roped in to help. We wanted to get some estimate of the distance of these things. And when radio waves travel through space, they pass a number of free electrons. And the free electrons cause dispersion, which makes higher frequencies arrive ahead of the lower frequencies. Terrestrial physicists have known this for a long, long time. If there's a lightning strike on the far side of the Earth, it generates a radio wave which travels around our magnetic field lines and comes down here. And if you listen here with a radio receiver, you can hear the radio waves generated by that lightning strike, but they come as what's called a whistler. Sorry. A descending note. The higher frequencies travel slightly faster than the lower frequencies, and you can measure the delay between the two, guess at the number of free electrons around this big loop of the Earth's magnetic field, and get an estimate of distance. So we can do the same kind of thing with our objects. We don't believe they're terrestrial in origin, they're keeping their place in the sky, but we could get an estimate of distance by seeing how spread out in frequency, how dispersed the signal is. So we set up for this observation. And it's technically a bit challenging because you've got to get everything working more or less at once. But John Pilkington, a postdoc, managed to do it, made a guess at the number of free electrons in space, and came up with a distance estimate, which put it way beyond the sun and the planets, but well within our own galaxy. Only one of, 100,000 million objects in our galaxy, but it's progress. It's still quite a puzzle because the pulses are quite short and steep and the periods are quite small, and these things don't seem to be getting tired. They keep pulsing at the same rate as far as we can tell. So what the heck is it? I mean, is it really little green men? 4 lots of little green men, different parts of the galaxy, all deciding to signal to planet Earth? No, that doesn't work. John Pilkington's efforts put the distance of these things as about 200 light years away. So that is well within the galaxy, but well beyond the solar system. I nicknamed these things little green men, which I do now rather regret, but it was an idea that was worth exploring. If it is little green men, they probably live on a planet which goes around their sun. As their planet goes around their sun, there will be Doppler shifts. So some of the time the periods will be shorter when their planet's coming towards us, and some of the time the periods will be longer when their planet is moving away from us. Jocelyn, keep making these fast recordings so as we can look for changes in the pulsar period. And Jocelyn kept making the recordings, and we couldn't find. But finding a second, a third, and the fourth really demolished the little green men hypothesis. There aren't 4 lots of little green men, all deciding to signal to planet Earth, all using a pulse technique. That just doesn't wash. It really has to be something more natural, even if Jocelyn has unfortunately nicknamed these things LGM 1, 2, 3, and 4. So that was all the pulsars that I found. Many, many more have been found. They're now up in the thousands, probably about 5,000. All the ones we know are either in our galaxy or in a very nearby galaxy called the little galaxies called the Magellanic Clouds. And there's probably now about, I don't know, many thousands, maybe as many as 10,000 of these things catalogued. They are fantastically accurate timekeepers. Nature has given us some wonderful clocks which we can use to do physics experiments. And for those who are seriously into physics, they have been used to confirm gravitational radiation, for example. They are really, really good clocks. So the picture we have of these objects now is of a very, very compact star, about 10 miles across. Weighs about the same as the sun, but it's all jammed in a ball 10 miles across. And the ball is spinning very, very rapidly, and it has a very strong magnetic field. And somehow, still I think not fully established, somehow, probably coming out of the poles, maybe coming from the equator, there are a couple of beams of radio emission which sweep around the sky like a lighthouse. And if the beam sweeps across the Earth, we see pulse, 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 pulse each time. In many instances, the beam will miss the Earth, so we're only seeing a fraction of all these known objects. And there's probably not much we can do about that, at least for the time being. So these things weigh much the same as the sun, which is a cool 1,000 million tons, all squeezed into a ball about 10 kilometers across. So the density is very, very high, extremely high, some of the densest things known, like the density of the nucleus of the atom. And they're believed to be largely made up with the fundamental particle we call neutrons. So they're also known as neutron stars. A thimbleful of that material would weigh the same as 7 billion people. The whole population of the Earth would counterbalance one thimbleful of the stuff from one of these stars. And you put that much material in a small ball and the gravitational force is huge. The work you do climbing a 1 centimeter high mountain on these objects is comparable to the work you do climbing Mount Everest here on Earth. The gravity, local gravity is so strong. And because the local gravity is strong, its atmosphere is very, very thin, something like that. So if there's little green men living on these things, they have to have their nostrils down in their feet. Very strong gravity, because there's so much material squeezed into a small space. It'll bend light, it'll bend radio waves. You can actually see over the horizon on one of these objects if you go to it. But it's not actually recommended that you go to one of these. Not too healthy for human beings. And little green men wasn't a bad idea because the gravity will redshift the light. So if these men were actually little red men, they'd look, no, I've got it the wrong way around, haven't I? Little blue men, they'd look to us like little green men because of the local gravity. And local gravity will also affect the way clocks behave and your heart. So clocks give 1 tick every 2 seconds, and your heart would do something similar if you were there, because it's distorting time with the very strong gravity. And there's also a very strong gradient of gravity. So if you go to land on one of these, and you're going to land feet first, because that's the sensible way to land. But as you come in, the gravitational force on your feet is significantly more than the force on your head, and your body gets pulled long and thin, and probably gets pulled apart. So great is the gradient of gravity. So don't go visit one of these. Whoops. There's a very, very strong magnetic field, we believe. 100 million Tesla. Your typical fridge magnet is about 1/100th of a Tesla, and a good strong lab magnet might be 10 Tesla. These are huge magnetic fields. And as they spin, they generate a huge voltage drop. So I wouldn't go there. I think not. You won't come back if you go there. And all that, all the material and all that magnetic field and everything spins like a solid body. It appears to be rigid. And so the pulse period that we see is actually the rotation period. So this whole star is typically spinning, about once a second or once every few seconds, which is fantastically fast. And we now observe pulsars. Some of them are in the millisecond range, so they're doing 1,000 revs per second. And the slower ones will sort of blip, 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 but still quite fast for something astronomical. They're extremely good timekeepers. They're far better than your watch, for example. Because when you get something that big spinning, it's the devil's own job to make it change its spin. It just keeps spinning, and the pulses keep coming. But they are very gradually slowing. So for a typical pulsar, the pulse rate has slowed by about 1 second since the age of the dinosaurs. They're really rather good clocks. And they have been used as clocks by physicists to test things like Einstein's theory of general relativity. And the name has caught on. Before we published the paper, we had some discussion about what we would call these things. The choices were pulsating radio star or pulsed radio star. And we opted for pulsating because pulsed might imply an agency making the pulses, little green men. And we didn't want to go down that route. So pulsating radio stars. After the discovery was announced, we were interviewed by many, many people. Lots more stories there. One of them said, "What are you going to call these things?" "Oh, pulsating radio stars." No, I mean, what about a short name? Short name? He said, "What about pulsar?" We already had quasar, so what about pulsar? We said, "Oh, yeah, not bad." So they became pulsars, thanks to the science correspondent of a rather right-wing British newspaper. And the name has caught on. You know that there are a make of watch called pulsars, good watches. Cars. I found some geraniums in the Netherlands that were called pulsars. And the name, has been adopted by a number of people and things. So these objects are very extreme and they set a number of records. The pressure at the center of one of these stars is that much bigger than atmospheric pressure here on Earth. The fastest known pulsar has a period of about 1.5 milliseconds. If you listen to it, it would whine. And look at the accuracy with which it's measured. Actually, they've now discovered one that's slightly faster. I haven't measured it to quite the same number of decimal places yet, but they'll get there. Some pulsars apparently have planets. If you study the pulsar period, you'll see there's some very small, slightly irregular Doppler shifts. It's changes in the pulse period. And it's because planets are tugging the star around a bit. And that's affecting the pulsar period that you receive. And they've managed to, so to speak, reverse engineering the problem and worked out that indeed there are 3 planets round this object. The left-hand half of the image is the Sun and the positions of Mercury, Venus and Earth compared with the pulsar, which is tiny compared with the Sun, and it's got 3 planets all really quite close in. There's probably also a 4th one as well. The roundest known thing in the universe is the orbit of a pulsar around another star. It's twinned, it's in a binary system with another star. And it's round to 5 microns in 500,000 kilometers, which again is stunning accuracy. An eccentricity of about 10 to the minus 7, and we can measure it. And if something falls onto one of these things, from, let's say, you're there and you drop your microphone or something, it hits the deck traveling at half the speed of light. Gravity is so strong that an acceleration in about a meter will get it up to a speed of about half the speed of light. So these objects are clearly very, very extreme. Thank you for your interest. Thank you for your attention. Thank you for the opportunity.
Thank you very much. Well, thank you for a wonderful lecture. Any questions or comments?
Is it known that it's the frequency that you're seeing? Is it known that it's the spinning, that you have the two conical shapes of the radio waves and not some other more complex shape that would give you a similar frequency but not the same kind of shape of the emission of the radio waves?
Generally speaking, we go for the simplest explanation. So that's why we opted for this explanation. There could be more complex ones that fit the data, but generally speaking, nature does the simplest one first.
So how come there's no pulsars on a nearby galaxy like Andromeda?
There probably are. We just haven't the sensitivity yet to pick them up.
If it's a neutron star and it's going very fast, right, and the gravity is very strong, why doesn't it implode and become a black hole?
Because it's made of extremely rigid stuff. The actual physics of the stuff is phenomenal. They've been able to work out a bit about what the interior structure is. And it starts off with a shell, probably of iron, to begin with, plus other tough stuff inside.
Thank you for the lecture. The one thing I'd love to know a little bit about was you talked about some pulsars that might have the radio emission from their equator. How does that work? Or at least how?
The question is about pulsars with emission from their equators?
Yeah.
Yeah, okay. Yeah. It's actually not very clear how pulsar emission works, period. Partly because everything is so extreme. Strong gravity, strong electric field, strong magnetic field, high rotation, you name it, they've got it. So the physics is actually pretty hard. And maybe in some instances you could get it from the equator, it's a possibility, but we tend to think of the magnetic poles, and maybe even with the magnetic pole so offset from the rotation axis that the north and south pole are close to the equator. Possible.
Well.
Okay, hi. Thank you for the lecture. So, one question I'm always thinking about is there any answers on why and how a neutron star will become, or like what could be some conditions for neutron star to become a pulsar instead of or just ordinary neutron star or magnetars and etc.
Right. Yeah, we now know of these stars in several other circumstances. In many instances we have one of these neutron stars twinned with an ordinary star orbiting it, and you may sometimes get X-ray emission from this object because its strong gravity is pulling stuff down onto itself, heating it and generating X-rays. So that's quite common. We still tend to think that the radio emission is associated with the magnetic poles.
So how, you mentioned a pulsar with an almost exactly circular orbit. How is that possible?
Many stars are what we call binaries, two stars orbiting each other. if this one is a big star, reaches the end of its life, does one of these big supernova explosions, core collapses, be one of the neutron stars. Sometimes that'll break up the partnership, but it doesn't always. And so you have one of these stars orbiting, one of these pulsars orbiting a relatively normal companion star. Does that answer? Mostly, yes, but it doesn't have to be. There's sometimes material between the two stars grabbed off the big one, and where there's material, there's friction, which tends to circularize elliptical orbits.
I'll pass the microphone to the back.
First, thanks for the great lecture. I was wondering what would cause the magnetic field axis to be aligned or misaligned with the spin axis.
I can only give you half an answer to that. Presumably in the original star, that was the way it was. And then when that original star exploded and the core got imploded, that misalignment was preserved.
Yeah.
Thank you again for the amazing lecture. I'm wondering what do we know about the accumulation of neutrons to form a neutron star, especially given that free neutrons are relatively unstable?
I'm not an expert in this area, but I believe that even though individual neutrons can be unstable, if you put a whole lot together, they're not necessarily unstable, I believe. And that would seem to fit the facts in that we've now been observing these objects for 50 years, and we don't see great changes in them in the 50 years, just a very, very gradual slowing of the rotation rate, which you might expect.
Right. Superb lecture. From your experience, what advice would you give to people who are supervising graduate students?
Will we allow other grad students to join in? Different people have different styles of supervision, it has to be said. Some are incredibly laid back, so laid back they're useless. Some are so engaged they're a menace, you know. It's actually quite hard to hit the right balance, to be honest, I think. And you seem to be very much left to learn how to supervise grad students. I've only ever had two, so I'm no great expert on this, but I think believe in your grad student is probably the first thing I would say. Don't automatically assume they're stupid.
Well, one comment that we made this morning is that it's a pity you did not discover the little green man, because your advisor could have gotten the biology Nobel Prize. Any more questions?
Thank you for the amazing lecture. Have neutron star collisions been studied with radio frequencies?
They've been thought about.
Yeah.
They've been studied in that sense. Whether they're common, how you would see them, I'm not very sure myself, to be honest. Distances between stars are so huge that collisions are very, very rare. The most likely thing you'd find is where you've got two stars orbiting each other. They might ultimately, lose energy and merge.
Thank you. So you mentioned that the Doppler effect can be seen with planets around a neutron star. Is there any effect on like binary systems and how they affect the timing of pulsars?
We know of some pulsars in binary systems. and we can get the orbits because of the Doppler shift on the pulsar period. I think we can probably also, fairly soon, if not already, measure changes in the orbital period as the orbits of the binaries evolve. They're really actually very good clocks, and we're typically measuring their periods to 7, 8, 9, 10 decimal places. Quite amazing.
Well, wasn't it recently used to detect gravitational waves?
Mm-hmm.
Maybe you want to comment?
That was a very interesting result. About what, 2 months ago, something like that, 3 months ago. Pulsars are actually very good clocks. They keep pulsing. And if anything disturbs that pulsar, maybe because it's orbiting, but even an isolated pulsar, if a gravitational wave comes by, you could think of this thing bobbing like, you know, the beach ball on the sea waves. And you can see the motion with a bit of good luck and practice. And one of the very recent results took a worldwide effort, although the results were only announced each continent separately, which was a bit of a shame, to detect a background of gravitational waves through studying the sort of bobbing motion of pulsars. It's a very difficult observation. It did need worldwide data, but for political reasons, each continent had to announce its own data separately. And frankly, when you split the data up into 3 or 4 different continents, the effect's hardly there, but never mind.
Okay, well, maybe we can thank Jocelyn again for a wonderful lecture.